In this video, we're going to summarize the chapter 19, and we are going to give you some hint about the homework of the chapter 19. Just make sure that you understand how to calculate the magnetic field force, and related problem, especially the application of the mass spectrometer. So these are the topics we are going to talk about. Let me just first review the topics that is important to this chapter. So the first topic is about the magnetic force. We compare the force between the magnetic force and the gravitational force and the electric force in the lecture. In this chapter, we are more focused on the magnetic force, but you are going to see a different force as well in the later part. Two different ways that you can create magnetic force, as you can see in this notes over here. So you can have a moving charge. The moving charge can create magnetic force. You can also have a wire with current. This would also create a magnetic force, and we have equation for each one of the cases. So for a moving charge, this charge that we're talking about is a positive charge. Okay, so the rule that we are using in this calculation is based on the positive charge. And we mentioned this in the class. If you have the negative charge, especially for the electron, then you are going to use the opposite direction to represent the direction of the force. So this is important. Remember, look at the problem and see if they give you a positive charge or negative charge. If they just say electron as negative charge, then every direction will be opposite. For the wire, the current direction is the direction. The current direction actually is a positive charge direction, so you don't need to do any of the opposite direction in the case of the current. Just follow the current direction will be the direction that you use to determine the force direction. So let's look at the first one here. And I also wanted to use the right hand rule to kind of mention how we can find the direction of the force. The first one that you see, the F over here represent the magnetic force. So F in the class we write F of B. So this is the F of B. And this F of B is due to a moving charge. So Q represents the amount of the charge. V is the speed of the particle. And then you have the B here is the magnitude of the magnetic field. The unit for the magnetic field is in Tesla. The speed is meter per second. And the moving charge, this is in Coulomb. So all this units should be consistent to the one that we write over here. And the unit for the force is so-called the Newton. So that is something that you have to be careful when you use this equation. Now, one other thing always confuse people is about the angle. So this angle is the angle that you look from the direction of the V to the direction of B. Okay, so this is a good time that we should draw the right hand rule. So let me just draw a right hand rule over here. So if this is a three-dimension stuff, so I'm going to draw three different arrows over here. The one at the bottom is the V, which is the direction of the velocity. And this is, I use thumb, so you can use the thumb to represent the direction of the B. The direction of the B is the magnetic field direction is the rest of the fingers. Okay, that's the rest of the finger you use as the magnetic field direction. And your palm is going to be your FOB. And the angle is the angle from V to B. So this is your angle. Theta is this angle here. So that is how you use the first equation right here. The second case is the case where you are looking at magnetic force due to a wire carrying current. Now it's actually the same idea of the charge is moving because current is actually charge in motion. So they carry the same idea. Um, in the book, they will derive the equation, and you will find out these two equations actually represent the same thing. To simplify this without going through the derivation, uh, you need to know when you have a wire, then you are given with the current. So the current is the I over here. Then we have a unit which is the amp. And the L represent the length of the wire. This one will be in meter. And then you also have the magnetic field, the B, which is in Tesla, right? So that is the unit for each one of this symbol over here. Angle, again, the angle is important. Now let me just draw another picture to show what that is. So let's say this is your wire, and let's make the current direction go this way. This is the current direction. This is your thumb. And then you are going to have magnetic field. That magnetic field, let's say, go this direction. This is the uniform magnetic field, and they go in this direction. And how do you determine the force? The force will perpendicular to both, so this will be your direction of the force. Again, this will be your palm. This is the fingers. And the angle is from the I to B, so this is your angle right here. Okay, so I hope that these two pictures shows you how to determine the angle of the magnetic force. This is also shows you two equations to find out magnetic force. The next thing we wanted to focus on is what about magnetic field itself. So we mentioned that the unit for the magnetic field is called the Tesla. It's actually a derived unit. So Newton divided by amp times meter. Actually, there's another one. This unit actually coming from the equation of the magnetic force. So it's actually coming from this force right here. Okay. You simply use the Newton divided by Coulomb and divide by meter per second. That also represent the Tesla. This one here you use the Newton divided by the amp divided by the meter, which is this one here, that represent the Tesla. Another important thing that you need to know about the magnetic field is that the direction of the field is from the north to south. A good comparison is about the electric field, which we will also look at this one too. Electric field, the direction is from positive to negative. Or you can say away from positive toward to the negative, the same kind of meaning. So from positive to negative is the electric field direction. Okay. We can use the ampere law to calculate the B due to a different configuration of the wire that carry the current. We actually shows you some of the cases. Let me just maybe just draw some of them over here, which we mentioned in the class. So the first case is just simply a wire, a straight wire with a current like this. Then magnetic field is going to be circulating around this wire and is going to be using the right hand rule. This again is your thumb. This is the curl of your fingers. Okay, so that is your field direction. The distance away from the wire is called R, and we can define the field as the mu 0 times the current divided by the 2 pi R. Okay. Another case that we see is several loops of a wire, and we draw this in the class. So this is the second kind of a situation, and let's make the current go this way, and this will be the total length of the coil of a wire, and we say there's like n loops in this coil. Then you can find the magnetic field for the loop of the wire that is equal to n times mu 0 divided by this L and times the current I. So this is the current I. Mu 0 is a constant. If we give you this in the exam, we will give you the constant. The last case is just like a circular loop. So this is a simple loop over here. Now you could have several loops. If you have several loops, you just multiply that number of the loops. Then this will determine by the direction of the current. If we make the direction of the current comes in from this direction, so current will go around like this and leave from here. Then you can use your right hand rule to determine the direction. You will find out everything in the outside is going to in, right? Cross represent in. Everything in the inside will be in. Okay. Now we're looking at a field which is at the center of this circle. Okay. So this B at the center. In this case is equal to mu 0 times I divided by 2R, where R is the distance from the center to the radius of this. So this is an R. If you have n loops, you multiply with the n. So this is the case if you have a circular loop of a wire, then you can find out the field at the center. Again, at the center is equal to this. So that's the last section in your book. If you wanted to understand more about that, you can look at the book. So this is something you have to understand. Right hand rule. Now I'm just going to use these two pictures to show you what the right hand rule is. So the right hand rule is simply to represent the relationship between velocity, field, and the force if you are looking at the moving charge. Again, this charge is positive charge. The second thing you can use the right hand rule is you can have a wire carry with current. So this is a current carrying wire. Then you relate the current direction, the magnetic field direction, and magnetic force. Yeah. You use the curl. So here I show you like two different pictures here. I'm going to show you two different pictures here. Okay, we both are based on the right hand. If you have a current, you wanted to determine the field direction, you use the curl right hand rule. So you use the thumb represent the direction of the current. This is the direction of the current, and the rest of the finger curl will represent your field direction. So this is the right hand rule to kind of determine a wire. How do you know the direction of the field generated by the wire? And it shows you the direction, like from where to where. Okay, so if this is the north, then here is the south. So because it's coming from the north to the south. If you wanted to find the force direction, and we say this is your F of B, This one is going to be your current direction or the charge moving direction. This is your field direction. So the book uses a different way, but I use this way. Um, Either way is fine. So if you want to follow my way, then you just use this way to find the direction. I the last thing that we talk about in the class is that we talk about the torque. So how is the torque generated? We use this figure to explain, right? So I hope that you still remember how we present this. It's based on the right hand rule. So your field direction is from the north to the south. So you can see this B over here represent the field direction is from the north to the south. And how what things that we represent field direction? The rest of the fingers, right? And then you also need to use the thumb to represent the direction of the current. Now, where is the direction of the current? If the current is right here, it's going up from the left bottom, so this is actually the current direction. Current flows in from the bottom on the left, then it will go around, so you can see on the left hand side it goes straight up. When it goes to the top, it goes to the right. And then you have to use each one of the direction to find out where is the force direction. And do this by yourself. You will find out, well, the first force direction on the left hand side is go into the paper, and the other side is this one here. The force will go out of the paper. So um, this one here is going out of the paper on the right, and on the left, that force is going into the paper. And the equation to find out how much of the torque is generated is based on this equation. Again, I don't want to spend time to tell you how we actually get these equations, but you need to know how to use this equation. Now, the tricky part of this equation is how you define the angle, right? So this angle phi here is the tricky part that most people might get wrong about this angle here. The angle is the angle of the area. So you're looking at the area. So if this is the case, let me draw a picture of the right hand side stuff. So um, over here we have this loop of wire, and this is the area we are talking about. The direction of the area is the direction perpendicular to that. Well, it's hard to represent that. Let me just say this will be the direction of the area perpendicular to the point. Um, so this will be the A perpendicular. And the field is going into the direction to the right. So you have the direction of the field go into the right. And then you have to find out, well, what is the direction, what is the angle between the B and between the A perpendicular. Okay, so so that's how you determine. Then you are using this B to this perpendicular as your angle here. So this will be the phi here. Yeah, and sometimes it's hard to visualize it. So the the presentation on this two dimension is hard to actually capture the idea, but try to understand how you can find the angle is important in this calculation. The unit for the torque is Newton times meter. So this is the unit for the torque. Okay, the last one, which is going to be one of the questions in your exam that I'm going to spend a little bit more time to explain what this is. the spectrometer, the mass spectrometer used in the chemistry. And the purpose of this one is to use the idea of the moving charge will bend, do a circular motion in the magnetic field. Okay, so normally the mass spectrometer separate into two parts. The one that you see at the bottom that marked with 1 and 2, that is what we call the velocity selector. So you have a section called the velocity selector. And the purpose of this one is that you only allow the particle that at a certain velocity be able to pass through, then goes to the top of this device. And notice here that we write not only the magnetic field. The magnetic field is B. We also have something that we just mentioned, which is this E over here. This E over here represents electric field. Okay, now if you have a charge that is moving in an electric field as well as the magnetic field, then this charge will experience two kind of a force. The two kind of force, one is the electric force, one is the magnetic force. How do we determine magnetic force? Same thing that you learned that we just show you the right hand rule. You can use right hand rule to find out the magnetic force direction. If you watch this video, try to think about how to find this direction of the magnetic force. In this case, at the bottom, by pausing the video. And now I'm going to explain how you find the direction. So use your right hand. The charge is a positive charge, so your thumb is going to go up, right? If you look at the picture right now, the direction of the moving charge will go up. The rest of the finger represent the field direction. So you have a circle dot. That means the field is go out, not go in, it's go out. So you have to flip your right arms such that the rest of the finger toward to yourself. So thumb go up, rest of the finger go out, your palm toward to the right. Therefore, this charge should experience a magnetic force that go in this direction. Okay, that is my magnetic force direction. Now, what about the electric force? Well, how can we have electric force? If you want to have an electric force, you have to have two charges, right? So, but we told you if you have an E field, that E field is from positive to negative. So you can think about you have a plate, and here this plate is positive. And you have another plate on the left hand side, this plate is negative. Okay, and you have a positive charge moving inside of these two plates, between these two plates, because this is a positive charge. What direction of the electric force will be? Well, unlikely attract, likely repel. So this positive charge will not move to the right because on the right hand side is positive. So you have electric force that goes to the left. So this electric force will go in this direction. That is opposite to the magnetic force direction. So you have two forces acting on this particle. If this two force is the same, and then you can make the charge moving forward directly pass through the gate, the aperture. And this is how the mass spectrometer control the field strength such that the speed will just move forward in this case. And because of that, because of that, and you are going to find a relationship between the forces. That relationship is this one here. Only the speed that is equal to the ratio of the electric field and the magnetic field that will pass through. So if we give you the electric field, we give you the magnetic field of this one here, then you will be able to find out what is the speed of this particle that will pass through. Okay, so that is the first part, the velocity selector. This is the idea about the velocity selector. Now be careful about this here. This is a positive charge. Now, maybe some of the cases or in the exam we will say, we're not using a positive charge. I use a negative ion. If that is a negative ion, then the force of the F of B will be on the left, well, acting on the left, and you have to make the field goes to the right, such that they can be balanced. If they are not balanced, then the velocity will actually bend. It's not going to pass through the aperture on the top. The next part of this is that once it goes to the top, so I'm looking at part 3 of this mass spectrometer. When it goes to the top, and you can again use the right hand rule, and you will find out it's going to be the same as the bottom, because your field also is going out of the paper and the charge is moving up. Field go out, use your right hand palm will force face to the right. So when your particle is moving, it doesn't matter it's at this position, or at this position, they always feel a force go inward like this. And that will make this one do a circular motion. And when they have a circular motion, they're going to have an acceleration. So your force is F of B. This F of B will make this particle to have a circular motion with the mass times a sub r, where a sub r is v squared over r, and f of b is qv times b. That's how we get this equation right here. Then you can simplify that, which will be this equation right here. So that tells you what is the object is determined by the mass. And we can look at the R, meaning where it lands on this detector. If you land detector at here or then detector at here, they will represent different mass. Then I can identify what kind of object that is, because each one of the particle has a different mass for different elements. Then we can use this one to identify. Okay, so that is the thing that we wanted to share with you, and wanted to make sure that you understand what those are. Okay, all right, let's move on to some example over here. Okay, now here are the homework problem that you're going to see. The first one is they give you a bunch of pictures. They want you to use the right hand rule to determine the direction. Okay. So one of the problems in your exam will be similar to this, or maybe more than one. You have to know how we represent symbol in the different direction. This one here, the circular one represent out. The cross represent in. So if we just use the first one for example, okay, and you have to determine what is the direction of V, right? So you have three different directions, B, F, V. So B is the rest of the finger go out. Use your right hand rule. The go out will face to yourself. And palm goes where it goes down. So you make your palm goes down and finger facing to you, you will find out your thumb is the direction of the velocity. And I believe in this case, it will goes to this direction, which is go into the right. Okay, so I'll let you do the rest of them. You just simply drag which one is the case of each one of the situation. They might have the same direction, may have different direction, but you have to make judgment which direction that should be. Alright, the next problem is to do some calculation. Now the second problem here, this probably doesn't require you to do it, but I wanted to use this one as an example. You're looking at a moving electron with a velocity in the xy plane at an angle of 30 degrees above the x-axis, and there's a magnetic field in the y direction. So when you have this kind of question, see if you can draw a picture to represent that situation. Let me draw a picture of what that means and see if you can think of how it was um, created. XY plane. So we have XY plane here. And they tell you the magnetic field is in the positive y. So my B direction is this one here. This is the B direction, the positive y. And velocity is in the xy plane, which is on the paper or on the screen. It has an angle 30 degrees above x. So this V is in this direction, and the angle is 30 degrees as opposed to the x-axis. So that's the information that you know. Now we want to find a force. If you look back, the equation that we use for this one here is Q, V, B, and the sine theta. Okay, what is the Q? Well, Q is an electron, so Q for electron is 1.6 times 10 to the negative 19 coulomb. That is your Q. The V is given, this one here, 3 times 10 to the 7. The B is also given as 3 Tesla. The question is what angle should be theta? And our angle is from V to B. So V is here to B should be this angle here. This is your angle. So your angle is actually 60 degrees in this case. Alright. Now, if we want to ask you a question about the direction, how do you represent the direction of the force? You use your right hand rule. And if you use right hand rule, the rest of the finger go up. Your thumb is toward to the right upper corner, right? And your palm should go facing to you, okay? So your palm should go out. However, this is a negative electron, so the direction is actually go into the paper, okay? So that direction of the force should be this way. Right, the next question that we want to show you as an example is what about an electron in a magnetic field? It will do a circular motion, just like a spectrometer. So when the spectrometer that you have, then the magnetic field is a uniform number, which is this one here. They tell you the speed of the electron is 189. This is the V. This is your B. And it travel perpendicularly to the field. And with this condition, it will go through a circular motion. We want to find the R. So if you go back to what we mentioned before, this equation tells you if a charge moving in the field, then it will have a relationship coming from this, which is the QVB equal to MAR, and we kind of summarize by eliminating some of the common terms. This give you R is equal to MV over QNB. So you just simply use these equation to find the result. Now, they didn't give you the N, they didn't give you the Q, so what is the N? N is the mass of this electron. That is 9.11 times 10 to the negative 31 kilogram. The Q here is the charge of the electron, which is 1.6 times 10 to the negative 19 coulomb. And the rest of the number are given, and you can find out what that is. Here they also ask about the frequency. So what does that frequency has to do with this? Well, the frequency has to do with the V, because this is something about the physics 1. We said if a thing is going through a circular motion, so you have an object going through a circular motion, where you have an R, which represent the radius of this circular motion. We can describe the motion in two different ways. We can describe the motion in terms of the angular motion, which is omega. This is the angular speed. And this angular speed will be equal to V divided by R, where V is the tangential direction of the velocity. So this is the V. And this omega is also equal to 2 pi f. So you can use this equation to find out what is f. Therefore, this f is equal to v over 2 pi r. So you can use, once you find out the v, well, v is given. Once you find out the r, you put that into this equation, you can find out the frequency. The frequency is going to be in hertz, so that's the unit for the frequency. Okay, the next question here, I send you the image, but after I look at this question, I think this question is a little bit challenging. No, not this one here. Oh, not this one here. The one that I send you, the image is this. Then you have a wire here. Then you have a rectangular loop of the coil at here, and we want to find out the force acting on this wire. Now, this will be a little bit challenging, was because if this is the wire with the current, then the field that we show you based on the Ampere law is going to be in this direction, and the equation for that field is a mu 0 I divided by I think it's 2 pi r. Yeah, 2 pi r. Now what is R? R is how much distance that is away from this Y. So if this one is R, now this one is not R, right? This one is further away. So what is the distance of this? They give you this one to be the W, so this distance is R plus W. I believe they put D in here, so this will be the D plus W. This was D, then you change to D plus W. So I decided not to ask you to do this problem. I take it out already. But let's look at this one here. So I have a wire I, and they tell you the length is L, and its current is 7.5 amp. I didn't show you the picture. Sorry, I forgot to show you the picture. This is the picture that I told you that I already sent you a figure, but we're gonna skip this problem, so I take it out already, so you don't need to worry about this. But if we look at this one here, this one is a wire carry a current, and the equation for that is I L B sine theta. Okay, theta is from the I goes to the B, so I to B. So you look at this case, what is my angle? The I goes straight up, the field is go in, so you flip your um, so if you use your right hand, you will see um, they're perpendicular. So in this case, theta is 90 degree, and you put rest of the number that you can find the answer for this. Okay, let's look at the torque problem and this one here. So this torque problem is that they give you a loop of wire. They tell you the side has a length of the S. They didn't give you the number. They tell you the loop has the field in the 1.5 Tesla. It's in the negative Y direction. So negative Y direction is this one here. This one is 1.5. But when you do your homework, your number might be different from this one. And the one I wanted to show you actually is how you determine the direction. Otherwise, the rest of the thing, you just simply use the equation. So what is the equation for the torque? When you have the torque, you're going to use torque equal to N I area times the sine angle, and B, sorry, forgot a B, sine angle. Okay, so N is the number of turn, which is this one here. T is 1.5 in this case. And what is the area? Well, area is S squared. What is I? I is at the bottom. They tell you I is 2.9 on the lower left. And what is the field strength? Well, it's also at the bottom here. The strength of the field is 0.18. Oh, wait, they give you two. Oh, this is not the field. This is a torque, which is tau. This is the tau. This is the I. This is the B. This is the N. Okay, now it looks like everything is given, but there's one thing that is missing, which is the angle. So how do we determine the angle? If you look at this one here, you will see two wires, right? One is this one here, one is this one here. That just simply represent the wire is actually is like a plane they cut into the screen with the angle that is 15 to the horizontal direction. So one side of the loop of a wire is goes in, the other side is the current goes out. So you can think about the loop of wire like this that go into the paper. And then what is the perpendicular direction to that wire? The perpendicular direction will be the direction like this. This is the area perpendicular direction, perpendicular to that wire. So then you look at the angle from B to area direction. So B to area, and this one here, this is your theta, and this theta is going to be the same as 15 degree. So in this case, theta is 15 degree. And then you can use the rest of the number to get the solution. Okay, oh yeah, here is the problem that I was telling you, so you can skip this one. I'm going to skip this one too. I wanted to just kind of look at the last problem over here. Okay, so here is the problem that we just mentioned about the max spectrometer. Then now this one give you all the number right here. Let's look at what other information they give you. First, notice they give you electron. Electron is a negative. So if this is a negative, first look at how this electron will travel in the velocity selector. We told you if you have a velocity selector that was a E field, the electric field is away from positive, so the positive on the top, negative at the bottom. And we wanted to draw the direction of the electric force, so that force should go what direction? You're using an electron, so electron carry negative, so negative should toward to the positive. So your F of E should go this direction. This is your electric force direction. What about the magnetic field direction? The magnetic force direction. Again, right hand rule. Thumb is the B direction to the right. The B field direction is go into the paper. So your palm should go up. However, this is an electron, so it's going to be opposite to your palm. Therefore, the direction of the magnetic force should go this direction. So this is of F of B. And you can see these two forces balance to each other such that the velocity will go straight until they go into the second part of this detector. What is the velocity? The velocity is going to be the ratio of these two, right? So you are going to use the ratio of these two field to find its force, to find its velocity. Once you find the velocity, then you use the next equation, which is the equation. So how do you find this first equation? The first equation is that F of E has to be equal to F of B. And F of E is equal to Q times electric field. F of B is QVB. So we find out the velocity is the ratio of E over B. So what is E? 9 times 10 to the fourth. What is B? 0.0055. So you got the velocity in meter per second. And the second part of this calculation is based on the circular motion, which is right here. The circular motion give you the QVB equal to M AR equal to MV squared over R. And then you find out, or R is equal to mv over qb. And but they ask you to find the m, right? So they give you the r, which is 4 centimeter. That will make this one be 0.04. What is the q? That's the charge of the electron. What is the b? It's a 0.0055 Tesla. Oh no, it's different. So VB is this one here, and the VC is different number. VC is 0.00225. So 0.00225. And your V is the V that you got from the previous part. Okay, so this is a mixed spectrometer problem. It's not super difficult once you get an idea. Now, I'm not just going to ask you how to find those values. I also want you to identify the directions. So um, I hope that you understand how to use the right hand rule to find the direction of the magnetic force. Also, for the electric force, you also need to know how to find electric force direction as well, based on the field direction. So this is our review for chapter 19 and also the homework problem. Hopefully that you understand these. If you have questions, please contact me or contact your tutor, and we will be happy to help you.